All right, we're going to do chapter 3 today. Chapter 3 is calculations with chemical formulas and equations. We're going to use molar masses, limiting reagent, theoretical yields, things like that. All right. All right, first thing we're going to do is molar mass. We did those calculations on the last test, except we used AMU. You have two isotopes, one's 40%, one's 60%, and then you get the molar mass, and that's the number you have on your periodic table. All right, so it is when you want a molar mass of a compound, you have to have the sum of all the atomic masses. So we found atomic masses for the last test. All right, and so if you have H2O, all right, so you got water, you got two hydrogens, you got one oxygen. So you look on the periodic table, and I'm going to say give them all the 2 decimal places. All right, so any number off the periodic table, like hydrogen is 1.00797. It's got a lot of decimals. You round it to just the 2 decimal places. And so you have 2 H's. Each one off the periodic table is 1.01. Now the units that you have to put for that is grams per mole. AMU is acceptable, but not very useful. So we are going to always use grams per mole. All right, there's 2 of them, so we have to multiply that by 2. All right, and then you look at oxygen, it's 15.9994. All right, so it is 16.00 grams per mole, and then you add them up. All right, and so you have 2.02 for 2 of these and 16 for that, and so the molar mass of water is 18.02 grams per mole. All right, so calculating a molar mass should be the easiest question on the test. You simply add up the atomic masses of the compound given. All right, so when you have a formula, you add up all the atomic masses that are in the formula. Whether it is a ionic compound or a molecular compound, it doesn't matter. You add up all the atomic masses and the units. The key, the only thing that people miss is the units. Make sure you know the units. They're grams per mole. All right, so again, I'm never going to ever write this part of any question. You always have to follow your sig fig rules, and you will give your sig figs accordingly. All right, so here you look up calcium, all right, on the periodic table. You look up oxygen, except you have 2 oxygens, so it's going to be 2 times whatever number that is. Then hydrogens, you have 2 hydrogens, and 2 times 1.01. This is 16.00, and calcium is 40.0 something. All right, and so you simply then add them up. Again, the key here is make sure you know when you're doing a molar mass that your units are grams per mole. The numbers, looking them on the periodic table, is very simple. It is the units that people get wrong. All right, so 40.08. All right, again, they're using AMU. I never use AMU. It is grams per mole. AMU is acceptable, but not at all helpful. Grams per mole, that is what we will use. All right, and then 2 decimals. So they gave 2 decimals for this one and this one, but they gave 3 decimals for the 2 hydrogens. And so I make the sig figs easier because that means that you're adding and you're subtracting. You're adding. All right, so you're adding. The rule is decimal places. So every molar mass will have 2 decimal places. All right, and so when you add this up, you always give it to 2 decimal places. 74.10 grams per mole is the only correct answer, unless, of course, it's not my problem. It's the problem from the computer that said give it to 3 sig figs. Again, I will never write that. You always have to give 2 decimal places for all of your molar masses, and every molar mass, whether it's the formula or the atom, it always has 2 decimal places. If you're worried about the multiplication rule, you can multiply this by 2 or you can add it 2 times. All right, so if you think I'm going to multiply this by, say, 10, and now I have 160, and so that would be 4 sig figs, and I should only give 160.0. My argument to that is I added up 16 10 times. So 2 decimals, 2 decimals, 2 decimals, 2 decimals. Again, if you give your molar mass 2 decimals, you have the right answer for sig figs. All right, so here you've got 1 carbon. So we did this on the last test. There's 1 carbon here. There's 5 hydrogens and 1 nitrogen. So 1 carbon, 12.01. 1 nitrogen, 14.01. Again, that's the number off the periodic table. Again, I'm not putting AMU. I am putting grams per mole. Always the units. I'll say it 100 times and you still won't get it. But anyway, it's grams per mole. All right, 5 times. Again, I don't use this, so my number is going to be different than theirs. So I put this as 1.01, and when I multiply it by 5, I get 5.05. All right, so again, the last decimal here, I'm going to have it as a 7. All right, you got 31.07, and I'm going to have grams per mole. They're going to have 31.1 because they said to give it to 3 sig figs for whatever reason. But if you added these up, you would get 31.06 grams per mole. Now remember how sig figs work. You give all certain numbers plus one final number having some uncertainty. So the number 31.07 and 31.06, those are the same answer. That error is in that last number. And that's what sig figs mean. All certain numbers plus one having some uncertainty. All right, so what is the mass in grams of the nitric acid molecule? All right, so here is where we're going to talk about atoms and molecules. All right, so atoms, extremely tiny. Atoms, extremely tiny. Molecules, extremely tiny. All right. When we're talking about the element of copper and the mass of the element, that's a whole bunch of atoms of copper. If we're talking about atoms of copper, we're talking about elemental copper. All right. And so we need a lot of atoms to work in the lab with a 5-gram sample of copper. All right. So the mass in grams of the nitric acid molecule is going to be extremely small. All right, and this is Avogadro's number, 6.022 times 10 to the 23rd. That is times 10 to the 23rd, extremely large number. This is atoms per mole. You will also see it as 6.022 times 10 to the 23rd molecules per mole. And in this chapter, you will not see it any other way. I don't think. Another possibility, if we're talking about ions, sometimes you will see it as ions per mole. That would be very rare. 99% of the time when you're using Avogadro's number for this test, it is going to be atoms or molecules per mole. Right? It's going to be atoms or molecules per mole, nothing else. If you put grams here, you got the wrong answer. There's no such thing as that many grams per mole. Atoms, extremely tiny. Molecules, extremely tiny. To get a mole of them, we need Avogadro's number, 6.022 times 10 to the 23rd. All right, so that number is given, but you have to know how to use it. You don't have to memorize the number, but you have to know, and it's just going to say per mole, because if you have a mole of pennies, you have 6.022 times 10 to the 23rd pennies. If you have a mole of anything, if you have a dozen of something, you got 12. If you got a mole of something, you got 6.022 times 10 to the 23rd. Again, you write that number out at 6, and then 0, 2, 2, and then, oh my gosh, ridiculous numbers of zeros. Okay, so this is an extremely large number. The only reason why we would need a number this gigantic is if we're talking about a tiny little atom or a tiny little molecule. All right, we need a whole bunch of those things in order to weigh it on our balance. All right, so the mass in grams of a nitric acid molecule is going to be extremely small. So we have 1 H, we have 1 N, and we have 3 O's. All right, so we have 1.01, we have 14.01, and we have 16.00 times 3, and we can add those up. So 48, 52, 53, 63.04 grams per mole. All right, so the only thing that we have is we always have the molar mass. Periodic table is always given. You always have the molar mass. All right, so the other thing that you have always is Avogadro's number. All right, and the only time you're going to use Avogadro's number is if the word atom or molecule is in the problem. If the word atom or molecule is not in the problem and you're using Avogadro's number, you have the wrong answer. All right. The only time you can use Avogadro's number is when we're talking about a molecule, extremely tiny, an atom, extremely tiny. Any other question would not be using Avogadro's number. All right, so we see the word molecule in the problem. And so we say, okay, we need Avogadro's number. And we need Avogadro's number, the one right here, the one that has molecules in it. And so we want the mass in grams. And so we have to have the grams per mole. We have moles, we have moles, we have molecules, we have grams. We have a conversion that we can do. So this is just like the last chapter. We have a molecule of nitric acid, one molecule. All right, and so if we have one molecule, all right, that is an infinite number of sig figs. We have one molecule. I have counted it. Very good luck counting it. It's so small you can't see it. But we have one molecule. All right, to get rid of molecules, we have to use the only conversion that we have with a molecule in it, and that's Avogadro's number. And here, if you're using your calculator wrong, you're going to get this wrong. So you got 6.022 times 10 to the 23rd molecules. All right, so that's how many molecules we need for a mole. All right, so I inverted it. So again, if you don't like that just being over mole, put the 1 in front of the mole. Put it divided by 1 mole. That's how many atoms you have in 1 mole. That's how many molecules you have in 1 mole. So if you don't like mole not having a number by it, put 1. All right, and so now we don't want moles. It asks for grams, but here we have 63.04 grams per mole. And so now my moles cancel the moles and molecules cancel the molecules. So it's just like the problems that we did for exam 1. All right, so you multiply everything on top, 1 times 1 times 63.04, divide by everything on the bottom, 6.022 times 10 to the 23rd. If you are not using your calculator correctly, you're going to get a giant number, which is ridiculous. The mass in grams of a nitric acid molecule is an extremely tiny number. And so whatever 63 divided by 6, that's 1 point something, 1.5. So let's say the answer is 1.5 times 10. That's going to be 10. That's minus 23. That's minus 22. Right? I think so. Grams. That's probably not enough sig figs. Anyway, all I can get is 1.5 times 10 to the minus 22, and the answer is... They don't give the answer? All right, well, they gave a question that I thought was a little strange because they didn't talk about Avogadro's number yet and said, what's the mass in grams of a nitric acid molecule? And then they gave the mass in grams of a mole of nitric acid. So anyway, I have answered the question that they asked. They did not answer the question that was asked. All right, if you want the mass in grams of a nitric acid molecule, one single molecule, that is a tiny number. And see how close I got to the right answer. All right, so it is 1 and then times 1, then divided by 6.022. And I never write times 10 in my calculator, E23. And then I multiply that by 63.04. And I get 1, well, I was off a bit, 1.05. I need how many sig figs? I need 4 sig figs, 1.047. So 1.047 times 10 to the minus 22 grams. All right, well, that was close, but I should have had my 1.0. All right. Figure out why. Oh, that's a 0. Okay, that's, yeah. Okay. It's 10.5. All right. So anyway, that is the wrong question for that answer. So the right question for the answer that they gave is, what is the mass in grams of a mole of nitric acid? Because that's what grams per mole means. That means grams in a mole. MOL is mole. MOL is not molecule. If you want molecules, you have to use Avogadro's number. All right, so moles, that's a mole. Avogadro's number, capital A sub capital N sub capital A, not NA, because that's sodium. So it is capital N and a capital A for the symbol for Avogadro's number. We will always use Avogadro's number, 6.022 times 10 to the 23rd. We'll always use it for sig figs. You don't have to memorize it. It will be given, but you're going to use it enough that you'll probably have it memorized. All right, but we will use Avogadro's number. The only time we use Avogadro's number, oh, they are going to finish the question. All right. All right, good. They're just taking multiple frames to do it. All right, so they have their grams in a mole. Now to get grams in a molecule, you have to divide by Avogadro's number, and there it is. So, and then you round that to 4 sig figs, and you get 1.046 times 10 to the minus 22. So they do answer the question. It just takes a few slides. All right, so the molar mass, carbon-12, isotope of carbon-12 is 12 grams per mole. So that's how we base our molar masses. But of course, there is carbon-13 and carbon-14. And so when you do your isotopic mass times the fractional abundance, and then you add all 3 of the carbon ones up off the periodic table, it is 12.01 grams per mole. So carbon is not 100% carbon-12, it's 99% carbon-12. And so your molar mass is a little higher because there is a small amount of carbon-13 and a very small amount of carbon-14. All right, so now you'll have lots of questions. So now we have 63.01, 02, 63.02. So we have 63.02 grams per mole. We already calculated the molar mass of nitric acid. You don't have to calculate it every time. One time is sufficient. All right. So, but you have to know that that is grams per mole. So here's a question that says we have 0.253 moles of nitric acid. We have 0.253 moles of nitric acid. And how many grams is this? So now we have the molar mass. You always have the molar mass. You have your periodic table always. And so that is 63.02 grams per mole. So 63.02 grams per mole. And so the moles on bottom cancel the moles on top. And you have your answer. So it's whatever, 17 point something. No, 16 point. 16. 16. Half. 32. Oh, yeah. Half of that is 16. Yep. All right. And so 3 sig figs is where we started with. And so you have to give 3 sig figs 15.9 grams. So there are 15.9 grams is exactly the same as 0.253 moles. If you take 15.9 and divide by 20.253, because this is grams of nitric acid, this is moles of nitric acid, you get 63.0. I haven't done it, but it better be, or you have the wrong answer. If you take 15.9 and divide by 0.253 and you push the button, you get, well, you actually get 62.8. All right, you get 62.8. All right, again, there is error in this last digit. Apparently that error is 0.2 because of rounding. So you've rounded, you've lost a 4 here. All right, that was pretty close to going up to 16. And if you put 16 here and you put 16 divided by 0.253, then you would be at 63.2. Right? So that's sig figs. You have 2 certain numbers and 1 number that has some uncertainty. And that number, we know the right answer is 63, so the uncertainty is a 0.2 standard deviation. All right. So we have 23.6 grams, and we want to know how many moles of calcium carbonate. All right. So they give you the formula of calcium carbonate. And so we have 23.6 grams, and we want to know how many moles. So we need to divide by grams, all right, because the grams have to cancel. And when you find a molar mass, it is, of course, grams, some number of grams, and always 1 mole. So the number 1 always goes with moles when you do molar mass. It is grams in a mole, grams per mole, grams per 1 mole, if you want to put the 1. All right, and so calcium was what, 40.08, carbon is 12.01, and then 16.00 times 3. That is calcium carbonate. 1 calcium off the periodic table, 1 carbon off the periodic table, and 3 oxygens off the periodic table. 48, 50, 60, 100.09 grams per mole. All right, so you have then your molar mass. So once you have your molar mass from the periodic table, then you simply know that you have to put it with the grams. That's how many grams. 100.09 grams is 1 mole. So you take your 23.6, divide by 100.09, and you get 0.236. So you simply just take your mass and divide by molar mass. All right, so when you have your mass divided by moles is going to give you molar mass. And so, because if you wanted to find the molar mass, if you were given the mass 23.6 and you're given the moles 0.236, that's going to give you the molar mass. So if you take your mass 23.6 and divide by your molar mass, and by your moles, 0.236 moles, you're going to get the periodic table number. You're going to get 100. Now, again, you have 3 sig figs and 3 sig figs. This number might be 99. This number might be 101. It might be 98. It might be 102. When you do 3 sig figs divided by 3 sig figs, you're getting 3 sig figs. If you don't round your number, you leave it all in your calculator, you will get exactly 100.09. But to get that number, this was equal to 0.2357877. Okay, so 3 sig figs. So we went from the 7.8 here up to the 0.236. And so you're going to have some error. But if you left that whole number in there and then divided by, you had your 23.6 divided by this entire number, you would get exactly 100.09. All right, so that is if you want to know an equation, it's very easy. Molar mass is grams per mole. All right, so this is mass, grams, this is moles. N is the symbol for moles. So your mass in grams divided by your moles. So that is grams per mole. It is the mass divided by the moles. All right. All right, so we're just going to take, again, 2.2 grams, and then we have to, again, divide by whatever grams we get for this per mole. So you got 6 times 12.01, you got 14 times 1.01, you got 2 times 16.00, and you have 1 times 14.01. All right, so you got to multiply that and add it all up. You got 6 carbons, 14 hydrogens, 2 oxygens, 1 nitrogen, periodic table. Push the buttons on your calculator, and you get your molar mass of 132.18. All right, always give the molar mass to 2 decimals. Sometimes it's 4 sig figs, sometimes it's 3 sig figs. This time it's 5 sig figs. Number of sig figs doesn't matter. It's always 2 decimal places. All right, would we get 1/8 the way we did it? 14.6.20. All right, so the way we would do it, when you add these up, it would be 132.20 grams per mole. So remember that the error is always in this last number. All right, and so apparently it's a plus or minus 0.02 because that's the 0.20, that's the 0.18. All right, so they only differ in that last decimal by a 0.02. All right, because the way the book does the sig figs for the molar masses is they give them all the 4. They give them all the 4 sig figs. All right, so anytime you have a hydrogen, you've got a problem. So I just say make everything 2 decimals, and it's always 2 decimals. But if you're getting a number that's slightly off from the molar mass that they're given in their answers, it is because they're giving 4 sig figs for hydrogen. All right, and so since the 2.2 had 2 significant figures, your answer will have 2 significant figures, and so you get a 1.7 times 10 to the minus 2 moles. So the number of sig figs is going to be determined by the question. So if the question says 2.2 grams and it's 2 sig figs, your answer is going to have 2 sig figs. Molar mass, well, should not be the limiting factor. The Avogadro's number should not be the limiting factor. But if they are, you're given 4 sig figs for your answer. All right. Okay, so when we read this, we have grams, and the question doesn't say moles. Here is where it says atoms. This should be a star. All right, it said atoms. Atoms. Anytime it says atoms or molecules, that's the only time. Anytime it says atoms or molecules, you write 6.022 times 10 to the 23rd atoms per mole. If the question's asking for atoms, then it's atoms. If the question is asking for molecules, it's molecules. If the question is not asking for atoms or molecules, do not use Avogadro's number. All right, so we have chromium. All right, and we have, so an atom is one thing. So a molecule would be like molecules of water, molecules of nitric acid, a molecule. All right, atoms are going to be of elements. We have an atom of chromium, we have an atom of iron, whatever. So this one is chromium. All right, and so we have 1.0 times 10 to the minus 6 grams. All right, and so we look up chromium, and we find on the periodic table that the molar mass of chromium is 52.00. So this is 52.00 grams per mole. And so you always have Avogadro's number, you always have the periodic table, and here is what they are giving you. They give you 1.0 times 10 to the minus 6. So it's 1 sig fig, so we know our answer is going to be to 1 sig fig. And we want our atoms to be in the numerator. So we have what we start with, which is 1.0 times 10 to the minus 6 grams of chromium. To get rid of grams of chromium, it is right here. It says on the periodic table there are 52.00 grams of chromium in 1 mole. of chromium. Again, I would highly recommend putting the 1 in front of the mole. It is always molar mass, mass per 1 mole. All right, grams of chromium cancel grams of chromium. We have moles of chromium. We don't want moles of chromium. We want how many atoms there are. And we see that there are 6.022 times 10 to the 23rd atoms of chromium in a mole of chromium. And so the moles of chromium cancel. And now you have atoms of chromium in the numerator. And so you have 6 divided by 52. Going to be so I'm going to guess 1.2 times 10. So that would be 7, 4, 16. My quick math is 1.2 times 10 to the 16 atoms. What do we got? 1.2 times 10 to the 16 atoms. That is correct. All right, so again, you have your molar mass, so the grams cancel, then you have the moles canceling, and when you multiply the numerators, divide by the denominators, you are left with atoms of chromium. So 1.2 times 10 to the 16, a large number. You need a lot of atoms to get even this small amount of mass. Atoms are extremely tiny. So when it says how many atoms, that number is normally a large number. All right, percent composition. All right, so we're going to have lead off the periodic table. We're going to have chromium. We just did that one, 52.00 grams per mole. Lead is 204 point something. Oxygen is 16.00 times 4. And what we're going to do is we're going to get our molar mass. And now to get the percent composition, of lead, you put the mass of lead. So you put the molar mass, the atomic mass of lead divided by the molar mass of the lead chromate. All right. M sub m is molar mass. M sub m, that is the abbreviation for molar mass. So if I write M sub m, that is molar mass. Right? So, and then times 100. So anytime you want a percent, that means it is then times 100. You would have to do the same thing, but this time chromium. You take the atomic mass that the oxygen gave, divided by the same thing. All right, and when you add up these percentages, they have to add up to 100%. So when you take the percent lead plus the percent chromium plus the percent oxygen, that's how you make lead to chromate. And so that has to equal 100%. All right, so the first thing you do is, it's not 204, it's 207. Okay, 207.2. All right, so again, they're given their number of sig figs as 4 for their molar masses. All right, that is not the rule for this class. 2 decimals. I don't know why they're giving chromium to 5 sig figs, but whatever. They have been consistent with 4 sig figs up to the chromium. They gave 5, and I don't know why. But anyway, off the periodic table, always 2 decimal places off the periodic table. All right, and so you don't have to worry about, oh, this was 4 sig figs and it's 1 decimal or whatever. Always 2 decimals, so you're going to have 323.20 grams per mole as your answer. All right, always 2 decimal places. I don't care what the book does. The rule is you do 2 decimal places for all molar masses, and when you add up 2 decimal places, and again, you can think this is a multiplication, or you can think that I'm adding 16.00 4 times. That's the way I think of it. And then you have 2 decimal places. All right. So now what we're going to do to get our percent lead is we take the 207.20 divided by 323.20 times 100. we take the 51.996 or the 52.00, which you should have, and you divide by 323.20. You take your 64, divide by 323.20. So you take the contributor for the lead, divide by the total. You take the contributor for the chromium, divide by the total. You take the contributor of the oxygen, divide by the total. And of course, to get a percent, you have to multiply by 100. We don't want the fraction, we want the percent. Then when you add up your percent lead, your percent chromium, your percent oxygen, which you should do every time, and make sure that that adds up to 100%. Because if it doesn't, then you forgot something. All right, so that's it. You take your lead. Molar mass of lead was 207.2. We only had one of them. All right, so you could actually put times 1 if you want. Divide by the total molar mass times 100. All right, we only had 1 chromium. All right, so the reason why we have 64 here is because we had 16.00 times 4. That is how we got the 64. All right, and again, when you add those up, you will get 100.00%. Make sure that you add those up. If you add those up and you get 100%, then there is a 100% chance that you got it right. Yeah, so there's their check. You check to make sure, and when you add those up, you get 100%. The only error that I see on this one is people will put 16 here instead of 16 times 4, and then they'll have the wrong answer for the oxygen. If they would add them up, they would see that that would not be 100%. You have to do all of the mass of oxygen divided by the total mass, all of the mass of chromium divided by the total, all of the mass of lead divided by the total. So percent composition should be a pretty easy question. All right, so here, now we're going to talk about an atom in a molecule. So we have sucrose. All right, sucrose is C12H22O11. How many grams of carbon are there in 68.1 grams of sucrose? There are a lot of ways that you can do this answer. I don't care how you do it. The way I'm going to do it is just from the last question. All right, if I know my percent carbon, then that's the mass percent of this 68.1 grams that is carbon. All right, and so I'm going to get my percent carbon, and then I know that 68.1 times that percent carbon, that is my mass of carbon. So if I had 50% carbon, then I would have 34.01 grams of carbon. All right, if I had 10% carbon, it would be 6.81 grams of carbon in the 68.1. I would just take the percent of that number. Now, to get percent carbon, I need my mass of carbon divided by the molar mass of the sucrose. And then to get percent, you multiply by 100. All right, so you have to take 12 times 12.01 for the molar mass of carbon. You need 22 times 1.01, that's the molar mass of hydrogen. And you need 11 times 16.00. You don't have to memorize these molar masses. The periodic table is given. And then you add them up. Let them add those up for me. So again, you got 12 carbons, so 12.01 times 12. You got 11 oxygens, 11 times 16. You got 22 hydrogens, and now we're going to add them up. All right, so again, we're going to get a different number than they're going to get because my number here is going to have a 2,2. All right, because I just used 1.01 here, and I'm going to have a 3,4 as my number and not a 3,0. Again, even though we have 22 hydrogens, again, the error is only in the last decimal. So you have all certain numbers plus the final one having some uncertainty. All right, so now we want the percent carbon. So we take our mass of carbon, which is 144.12, divide by the mass of the molecule, which is 342.30, and we multiply by 100, and we would have our percent carbon. And then we simply take whatever that percent is, put it in fractional form, and multiply it by the 68.1. All right, so they didn't actually do the percent. All right, so they just got the fraction. Here's the fraction. So you take your 144.12 and divide by the 342 point, I'm going to use 34 because that's what I got. And that is a 42.10, okay, 42.1%. So this is when you take the 144.12 grams divided by the total, 342.30 times 100, you get 42.1% carbon. All right, so in sucrose, 42.1% mass percent. All right, when you're taking the mass divided by the mass, that is the mass percent. All right, and so then I need 42.1% of 68.1. The answer is 42.1% of 68.1. So you have to convert that to the decimal form. So 0.421 times the 68.1 grams equals 28.7 grams of carbon. All right, so I will get the percent, and then I will take that percent, so 68.1 grams, I want 42.1% of that. That is less than half, so I know it's going to be less than the 34. Yes, 28.7 grams of carbon. Yes, that works out exactly the same in sig figs. All right, so percent composition. When we are doing our percent composition, what you're going to do is you're going to go to the lab and you're going to make a compound. And then you need to know the percent carbon and percent hydrogen. If you have a new compound, you always will send it off or do it in the lab to find your percent carbon and your percent hydrogen. All right, and we do this by complete combustion. So we're going to take this compound that contains carbon and hydrogen and we are going to burn it. When you burn something, you produce CO2 and water. So when you do complete combustion, you always get carbon dioxide, water, heat, light. All right, so you have CO2 and water. Those are the chemical compounds in the balanced chemical reaction. We are going to burn it. It's going to produce carbon dioxide, and we're going to produce water. All right, and we're going to capture our carbon dioxide and our water, and we're going to weigh it. All right, so there's a lot of traps that will trap all the CO2. You weigh it before, you weigh it after. It's going to weigh more because it has trapped some CO2 in there. We got a lot of different water traps. Again, you weigh it, you run the experiment, and then it's going to trap the water in there. You weigh it, you get your mass of water. And then from that, we can get our percent composition. All right, so here is one that's not an unknown. Usually when we're doing this, it's an unknown, but we got to practice, make sure we're doing it correctly. So benzene, that is a liquid. That is an organic liquid. All right, so we weigh out 342 milligrams and we burn it. All right, so we have 342 milligrams of benzene and we're going to burn it. We have excess oxygen and it completely burns and we get carbon dioxide and water. All right, so we have our carbon dioxide trap. We weigh it before and after. We do the subtraction and we see that 1,156 milligrams of carbon dioxide was produced. All right, now that's all we need. Normally you will get the amount of water, but in the reading up here, it says benzene is a liquid compound composed of carbon and hydrogen. We only need the percent of one. If it's 40% carbon, then it's 60% hydrogen. If it's 10% carbon, it's 90% hydrogen. It only contains carbon and hydrogen, which means those two percentages add up to 100%. If it didn't say that, which it usually does not, you would also have a mass of water and you would find the percent carbon and the percent hydrogen. All right, this time you don't have to because there is only carbon and hydrogen. So what we're going to do is find out how much carbon is in this amount of carbon dioxide. All of the carbon that's in here came from the unknown or came from the benzene. We know what it is. All right, so all of the carbon in the 1,156 milligrams of carbon dioxide, all of that carbon came from the benzene. And so we have to figure out what that is. So we need percent carbon in carbon dioxide. All right, so you take your 12.01 and your 16.00, multiply it by 2. You got 32, 42, 44.01 grams per mole. All right, so that's your CO2. 1 carbon, 2 oxygens, periodic table, molar mass 44.01. All right, so to get the percent carbon, you simply take the 12.01 grams per mole of carbon, that's your carbon, divided by the molar mass, 44.01 grams per mole, CO2, times 100. You take your 12.01, divide by your 44.01, you get 27.29%. All right, and if you do this a lot, you'll have that memorized because you need that number every time you do a elemental analysis. All right, so we know that 27.29% of this 1,156 milligrams is carbon. And so we take our 1,156 milligrams, we take the 27%. To get 27% of that, you have to convert it to decimal form, 0.2729. And that gives you 315.5. 315.5. So that's how many milligrams of carbon are in 1,156 milligrams of carbon dioxide. And we know that all of that came from the benzene. And so to get the percent carbon in benzene, we take the mass of carbon, 315.5, divide by the mass of our benzene, which is 342, and multiply by 100. And that gives us 92.2%. If you clear the calculator, it would be 92.3, rounded correctly, percent. All right, so again, when you give me the answer, and if the key says 0.2 and you get 0.3, or the reverse, if you get 0.3 and the key says 0.2, I know that the error is in that last digit, and I check to make sure you did your work correctly, and normally it's because you rounded something, and you cleared your calculator and plugged it back in. Because if you put these numbers in your calculator, you get this number. If you don't clear your calculator and leave the 315.4 whatever it was, number, 46, whatever, then it would be 92.2. All right? So the percent carbon, if it's 92.2% carbon, then we have a 7.8% hydrogen. If it's over here, you got a 7.7% hydrogen. All right, because we know that it states that it only contains carbon and hydrogen. So those two numbers have to add up to 100%. Let's see if they get 92.2 or 92.3. 92.3. All right, so they clear out their calculator. And so again, if you plug this into the calculator, you get 92.3. If you do not clear your calculator, you would get 92.2. But either answer is 100% correct. The error is in that last digit. Right. And then, well, they do it a different way. I would not do it this way. But it could be the question. And what's your percent hydrogen? That could be the question. 7.7%. Simply know that they have to add up to 100.0%. If it said how many milligrams of hydrogen is in this sample? Well, we know that the total is 342. So you would take your 342, subtract the 315.5, and if you did sig figs, you would have a bigger problem here. But anyway, 26.5. If you take your 26.5 and you add your 315.5, you actually get 342.0. All right, so once we find the formula, and so when you do benzene, and they have an example down here as well, benzene is C6H6. So that is the molecular formula of benzene. The empirical formula, so this is molecular. The empirical formula is the simplest ratio of the atoms. And so when you look at benzene's empirical formula, it is simply CH, which means there's, for every one carbon, there's one hydrogen. That is the simplest formula. The molecular formula for benzene is C6H6. All right, so they give examples down here. If you had a molecular compound of dinitrogen tetroxide, its empirical formula would be a 1:2 ratio. For every one nitrogen, there are two oxygens. If you wanted the empirical formula of hydrogen peroxide, it is HO. For every one hydrogen, there is one oxygen. It is the simplest ratio, whole number ratio of your atoms in a molecule. That is the empirical formula. All right, so we are going to be given a bunch of percentages. So we had the 92.3% carbon and then the 7.7% hydrogen. So this is benzene, the one we just did. All right, so they're not going to tell you maybe it's benzene. They're just going to say calculate the empirical formula. In order to determine an empirical formula, here are the steps. Number one, you assume any amount you want. All right, any amount you want. Highly recommended that you assume 100 grams. Why? Because if we have a 100-gram sample and it's 92.3% carbon, then we have 92.3 grams of carbon. And we have 7.7 grams of hydrogen. So if you assume a 100-gram sample, your percentages are going to then be grams of that amount, because this is 100% and this is 100 grams, right? So if you assume, when they're giving you percentages, you assume a 100-gram sample. If you want to assume a 57-gram sample, it works the same, except you have to multiply it by 67, 57, whatever. Use any number you want, you will get the right answer. The easiest number is 100, because then the 92.3% becomes 92.3 grams. If you want to use 1 gram, it's 0.923 grams and 0.077 grams. You can use any amount you want. 100 is the easiest. So there's nothing special about this number 100. It's just the easiest way to do it. Convert to grams, all right? It is grams now. So now convert it to moles. So then to convert grams to moles, you divide by the molar mass, 12.01 grams per mole of carbon, and 1.01 grams per mole of hydrogen. All right, so then is when, so the first two things are pretty easy. 100-gram sample, they're now grams. Convert them to moles. So you simply divide by the molar mass. So when you take your 92.3 and divide by 12.01, you get 7.69. So 7.69. When you take your 7.7 and divide by 1.01, you get 7.62. All right, so this is not a very helpful thing. So then, number 3 is you divide by the lower number of moles. So you divide by the lower number of moles. Or if there's lowest, yeah, so if you have more than one, lowest number of moles. So if you have just two things, okay, smaller number here, is 7.62. Lower number here is 7.62. So you simply divide by the lowest number of moles. And so the one that has the lowest number is 1. All right, and when you take your 7.69 and divide by 7.62, you get 1.01. Okay, so this is also 1. So then you go to the whole number. That's a 1, that's a 1. And so then, oh, they do say that. Okay, fine. So 3 is to manipulate, and I guess they go through the rules later. And so now you have a 1 carbon to 1 hydrogen, but when they're 1s, you don't put them. So it's CH. So when you have the empirical formula for benzene, it is simply CH. All right, so here it is. Manipulating the ratios. Divide each mole amount by the smallest mole amount. All right. In the case of benzene, we got 1 and 1. All right. It doesn't usually or doesn't always come out to be whole numbers. All right. So if it is not a whole number, you're going to have to multiply each mole, every single mole, by some factor to make every number a whole number. So if you had divided it, you would have got something that was 0.5. In order to get rid of a 0.5, you multiply all of them by 2. So if you had a 1 and a 1.5, then you would have a 2 to 3 mole ratio. All right. So if 1 was 1 and 1 was 1.5, when you divided by the smaller number, then you would have to multiply not just the 1.5 by 2, but also the 1 has to be multiplied by 2. Each number of moles has to be multiplied by the factor. If you got a 1 and a 1.33, then you got to multiply them both by 3, and you would have a 3 to 4 mole ratio. If you had a 1 and a 1.25, now you got to multiply both of them by 4 in order to get a whole number, and then you would have a 4 to 5 mole ratio. All right. So 0.33, that's 1/3. A 0.67, that's 2/3, and that's why we're multiplying those by 3. 0.25 is 1/4. 0.75 is 3/4, and that's why we are multiplying them by 4 to make them into whole numbers. All right, so if we had 0.2, I think we only go down to 0.2. If you had 0.2, you would have to multiply by 5. All right, so or 0.8, because 0.2 is 1/5, 0.8 is 4/5. All right, to get rid of that, you would have to multiply by 5. Anything less than 0.1, round it to the whole, or 0.2, round it to the whole number. So if your number is, if it's less than 0.2, all right, or higher than 0.5, then 0.5, then 0.8. All right, so 0.2, 0.8. So 0.2, you just get rid of it. You round it to the whole number. So if you had a 1 to a 0.95, that is a 1 to 1. You round it. If you had a 1 to a 1.1, that is a 1 to 1. And so we go, if you had a 1 to a 1.15, that is a 1 to 1. If you had a 1 to a 1.85, that is a 1 to 2. All right, so if it is greater than 0.8, you just round it to the whole number. If it is less than 0.2, you round it to the whole number. If it's 0.5, you got to multiply everything by 2. If it's 0.33, multiply by 3. 0.25, multiply by 4. 0.2, multiply by 5. All right, we already did benzene. All right, so again, you get your two numbers, and then this one was 1.01, which is going to round to a 1, and so it is a 1-to-1 empirical formula. In order to go from empirical formula to the molecular formula, because we know benzene, because I told you benzene. Benzene is C6H6, and the empirical formula is CH. We can find the empirical formula. We'll have information, and we can easily find the empirical formula. The only way that you can get to the molecular formula is to be given the molar mass. To go from here to here, you must have the molar mass. And so the problem is going to say calculate the empirical formula, and then it's going to say the molar mass of that compound, and they're going to give you a number, and then it's going to say find the molecular formula. All right, and so you're going to have an integer that you're going to have to multiply by. So you're going to take the molar mass that has to be given and divide by the empirical mass. And that's going to give you an integer n. So for this example, your molar mass is C6H6. So that's going to be 12.01 times 6 plus 1.01 times 6. So you've got your 72, 78. And so the molar mass there would be 78.12. All right, and then you would take your empirical, which off the periodic table, 12.01 and 1.01, 13.02, and so you divide by the empirical mass, which is 13.02. All right, grams per mole. And when you push the buttons on your calculator, this is always an integer. If you do this and you don't get an integer, one of your numbers is wrong. All right, anytime you take the molar mass that's given divided by the empirical mass, you will get an integer. Now note, if it was 5.9, that's equal to 6. All right, if it was 6.1, that is 6. All right, it's not going to be exactly 6. You know, it might have to round. Again, the same rule. As long as it is between the 0.8 and the 0.2, you just round it to the whole number. And if it is not between those, then you did something wrong because it has to round to a whole number. All right, so here it is here. You take your molar mass and divide by your empirical mass. All right, so you take your 78.1, the molar mass. All right, so benzene. Right, so here's the problem. They're always going to give you, and they might give it to you in AMU. I'm never going to give it to you in AMU. It's going to be in grams per mole. It's the same thing. Grams per mole is what we need it to be in to do all of our conversions. AMU is not helpful. All right, so I'm going to say it's 78.1 grams per mole, and you have CH. So 78.1, that is your molar mass, divided by the empirical mass. 12.01, 1 carbon plus 1.01, 1 hydrogen. That's where the 13.2 comes from. And that has to give you an integer. And so when you take your C1H1 that you don't put the ones for, and you multiply it by 6, you can do everything right. And if you say the molecular formula is 6 CHs, that is the wrong answer. Or if you say it is CH and then sub 6, that also is the wrong answer. The only correct answer is C6H6. So when you multiply this by 6, this is a 6 and this is a 6. The only correct answer is C6H6. You want to give me the correct answer when you do this or you do this, but that is not the correct answer. That is not how you write a molecular formula. All right, so I'm going to not give you the name of the compound. I'm going to say an unknown. Is composed of 34.5% sodium, 23.3% phosphorus, 42.1% oxygen, and calculate the empirical formula. So you have to know your steps. Number 1, I always do a 100-gram sample. Again, any size sample is fine. If you're not doing 100, I don't know why, but whatever. You will still get the same answer. Then we're going to convert to moles. And then we're going to divide by the smallest number. And then we're going to have to determine if we need to multiply everything through. If we get a whole number for all three of those, then we're done. If we don't, we have to multiply by 2 or 3 or 4 or 5. All right, so if we have these percentages, now they're grams. 34.5 grams of sodium, 23.3 grams of phosphorus, and 42.1 grams of oxygen. All right, and so we have 22.99 grams per mole for sodium. We have, I don't know what phosphorus. We have 16.00 grams per mole for oxygen. P31, 31 point something. 30.97. 30.97. All right, so when we push the buttons, 34.5 divided by 22.99, we get 1.5, 0. When we take our 23.3 divided by the 30.97, we get 0.75. 0.752. And when we take our 42.1 and divide by 16, we get 2.63. All right, so that's number 1, 100-gram sample. Number 2, convert to moles by dividing by the molar mass that you find on the periodic table. Number 3, divide by the smallest number. So we're dividing everything by 0.752. Divide everything by 0.752. Divide everything by 0.752. All right, so that is obviously 1. And this is obviously 2. And so divide by 0.752. And that is a 3.5. All right, so we got a nice integer, we got a nice integer, we got not nice integer. All right, so what are we going to do with 2, a 1, and a 3.5? To make them all integers, multiply by 2. So when you have a 0.5, then to get rid of that, you have to multiply not just the 3.5 times 2. All of them have to be multiplied by the same integer. And so you're going to have 4 sodiums, you're going to have 2 phosphorus, and you're going to have 7 oxygens. And so your answer is Na4P2O7. Right. All right, so this time they give you the molar mass in grams per mole. That's AMUs, grams per mole. All right, so here is a question. Again, I'm not going to give you hexamethylene. Hexamethylene. Okay. Hexamethylene diamine. All right, hexamethylene diamine is one of the materials. They left off half of the compound name, so good luck getting the answer to hexamethylene, which has no nitrogen in it. All right, is one of the materials used to produce nylon. It is composed of 62.1% carbon, and again, all of this information is not needed. I would say an unknown. It's composed of 62.1% carbon, 13.8% hydrogen, and 24.1% nitrogen. The molar mass of this compound is 116. Calculate its molecular formula. On the test, it's going to say calculate both its empirical formula and the molecular formula. All right, so we're going to do exactly the same thing we did before. A 100-gram sample, convert to moles, and then divide by the smallest. All right, so we converted it to grams because we have a 100-gram sample. So we have 62.1 grams of carbon, 13.8 grams of hydrogen, 24.1 grams of nitrogen. To convert it to moles, we divide by the molar mass. Carbon, 12.01. Hydrogen, 1.01. Nitrogen, 14.01. And we get our moles. All right, and then we look at the three numbers and divide by the smallest number that we have, which is a 1.720. 1.720. 1.720. So you have your 3 moles, divide all of them by the smallest one. And when you do, it works out very nice. Everything is already an integer. And so you have your empirical formula, C3H8N. So the molar mass was given as 116. And so we have to then divide by the empirical mass, which is 12 times 3, 36, plus 8, 44, plus 14, 58. And so when you divide that by 58, you get 2. So you take your molar mass divided by empirical mass, and you're going to get an integer. And that integer is a 2. And so the only correct answer for the empirical to molecular formula is to multiply all these numbers by 2. Not putting a 2 out in front doesn't do it. You have to have C6H16N2, the only correct answer. So when you get the 2, make sure you know what to do with the 2. It is C6H16N2. All right, and we will do stoichiometry tomorrow.